Hi everyone. My name is Vijay Balaji and I am delighted to present the Poisson distribution, a fundamental concept in probability and statistics. In some few minutes, we will delve into the definition, history, characteristics, application, and practical examples to understand how it helps us to analyze the rare and random events in this various field. So, definition. It is a discrete probability model that calculates the likelihood of a certain number of events occurring in a fixed time or space interval given a constant average rate. For instance, it is used to predict like how many customers will arrive at a store in an hour, the number of website clicks in a minute, system failures over a period. This ability to model rare event makes the Poisson distribution essential in fields such as business, artificial intelligence, and data science. So here it comes the formula with the probability mass function as like Px is equal to x, which is equal to e power minus lambda power x divided by the x factorial, where the Px is equal to x is the probability of observing the exactly x event, and lambda is the average number of events in the interval, and x is the number of occurrences of the event, and e is the Euler's number, which is having a value of 2.71828, and the x factorial. So, history of the Poisson distribution. It was introduced by Simon Denis Poisson, a French mathematician, in 1837. He developed this distribution to analyze a legal probability such as likelihood of errors in court judgment. While originally rooted in judicial process, it was soon adopted across various domains due to its practicality in the modeling rare events. By early 20th century, it became the widely used in fields like business, economics, and applied mathematics, forming a critical component of modern probability theory. Key characteristics of the Poisson distribution. Now let's explore about the unique characteristics in it. Single parameter. The distribution is defined by lambda, the average rate of events. Mean and variance. Uh, it does have a remarkable probability that both the mean and variance are equal to lambda, and memoryless probability, sorry, property. The distribution assumes that the occurrence of an event in one interval does not affect the probability of events in another interval. And skewness and shape property. For smaller lambda values, the distribution is positively skewed. However, as lambda increases, the distribution becomes more symmetrical and eventually resembles a normal distribution. Yeah. The Poisson distribution is also closely related to other distributions. So, the Poisson distribution versus binomial distribution. Actually, it arises as a limiting case of the binomial distribution when the number of trials is like very large, up to infinity, and when the probability of success is like very small, is equal to somewhat zero, nearer to zero, and so that the product n into p, which is the lambda, remains always constant. The exponential distribution, it is the process of visualizing the event in a particular time intervals. It seems to be like having a relationship with the Poisson distribution, while the Poisson distribution calculates the outcome of the number of events happening in the time interval, so that the probability distribution function x is like lambda into e power minus lambda x, where the x is like lying in the limits 0 to infinity, and the mean is like 1 by lambda, so and the variance will be like 1 by lambda square. So here we come with an example problem. Uh, the customer service representative receives an average of 6 emails per hour. Assuming that the number of emails follows a Poisson distribution, what is the probability the representative receives exactly 4 emails in an hour? So here the lambda average rate will be like 6, and the decision number of emails will be like 4. So while we are like substituting this value in the formula, we are will be getting like the value which is like 0.1339, so that on converting it to the percentage, we'll be getting like 13 percentage point 3 13.39 percentage. And here we go to another example. A manufacturing process produces an average of 2 defective items per day. What is the probability of producing at most 1 defective item in a day? So here the average, that is like the mean would be like 2, and here we are supposed to find the at most one defective item, so that it's like 1 and below that. So here the x will be like 0 and 1. So we should separately calculate the value for 0 and 1, like the probability of x is equal to 0 and the probability of 1 is equal to 0. Once we like by substituting this in our formula, and once we find that, we can like add this both, and thus we would be getting an answer like 0.4060. That is the 40.6 percentage. So this is the answer of it. And it does have like applications. So it has been used at numerous fields. First will be like business. It helps in inventory management, customer demand prediction, and risk analysis. And economics, economists use it to analyze the market fluctuations and model economic events. At artificial intelligence and data science, it is like a vital for modeling rare events, predicting customer behavior, building machine learning algorithms. So these applications demonstrate how the Poisson distribution bridges theory and practice, providing valuable insights for decision making. Assumption and limitations. While the Poisson distribution is powerful, it relies on certain assumptions. So the independent events should occur independently of one another. Constant rate. The average rate, that is lambda, must remain consistent over the interval. However, it has limitations. It's the limitation, like it's less effective when events are dependent or when the rate of occurrences change significantly. So understanding these constraints ensures we use the model appropriately. Conclusion. In conclusion, the Poisson distribution is an elegant tool for understanding rare and random events. Its simplicity, combined with its wide applicability, with its indispensable in fields like business, data science, and AI. By adhering to its assumption and recognizing its limitations, we can use it to make informed decisions and solve complex problems. So, thank you.